Welcome everyone to the final talk before the afternoon tea. So this is Micropython Gotcha by Michał, and give us warm welcome to him.
Yeah, hi everybody. So welcome to the last talk before the afternoon break. It will be about the Micropython from the bit more beginner's perspective. So what can you spot when you try to fiddle with Micropython on different development boards? So who am I? Well, as you can probably judge by the picture, I'm a serious software developer. And I came here from Poland, so quite a long journey. If you want to contact me, there are all my contact details. I slightly prefer email, but I guess Twitter will also do. And my whole professional life is about C, Linux, and Python. The proportions tend to change, but it's usually about these three things. I've been around in the software industry for, well, I guess about 14 years now. So let's start from a bit different angle than all the Micropython talks during this conference. So let's talk about happy hacking. So actually what hacking is, accordingly to my favorite knowledge source, which is Wikipedia, hacking is the act of engaging in activities such as programming in the playful and joyful and explorational way. And this was actually what was our aim when me and a couple of my friends attended to a hackathon called Hack.ye, which is the biggest stationary hackathon in Europe. And after quite a few hours of coding and possibly a few liquid refreshments, we had, well, the idea emerged. Well, every project is better when it has a thermal printer. So, well, the hackathon came to an end, but the idea somehow stayed with us and it materialized. It materialized as an object. Well, the object was small and it was definitely a thermal printer. You could power it by, well, any DC adapter that you have laying around in your home. It was communicated over UART. If you're not familiar with what UART is, I will explain that on the next slide. And there was a Python library for that. So it was just enough to start happy hacking. So UART is the Universal Asynchronous Receiver Transmitter, aka serial port. So you have two lines. One is for transmission. The other one is for receiving the data. Actually, if you're talking to the printer, one line is enough. The printer itself is not too talkative. So let's run it. It occurs that the guys from Adafruit actually prepared a library that's meant to be used with this very printer. It's almost pure Python, and it works out of the box. So I just connected it to the Raspberry Pi and ran it. And it occurred that it just works, but it's not much of a challenge. So a friend of mine thought that he will port it to Micropython. So he prepared a Micropython port of this very library, and he put it on GitHub. So he needed to make a few changes. The first one was to remove all the Python 2 code, as Micropython runs a Python 3 code. Well, he replaced this serial module, which is not available for Micropython, with the machine UART, which is the standard way to deal with the serial communication in Micropython, and removed the capability of printing images, as it was based on PIL, which is using C pretty heavily. So he just wanted to have it running purely in Python. And he ran it on the PyCon's LowPy version 1 board. So it is a board that runs Micropython, and it actually works. So let's have a look what actually the PyCon's LowPy v1 is. So this is the ESP32 based board, which is meant for the LoRaWAN, which is the long-range wide area networks. But it has 2 UART ports, and it has 512 kilobytes of RAM and 4 megabytes of flash. So it was enough to steer the thermal printer. And as we had this implementation running, I thought that we can go lower. Actually, I thought about connecting it to ESP12E, which is the well-known Wi-Fi module that you usually use to communicate with the serial line with the AT commands. But it appears that inside there is a ESP8266 microcontroller, so there is a Micropython port for it. So comparing to the other board, the processor was different, but hey, we're just going to use the serial port. And it had a slightly less RAM. Spoiler, it will have an influence. And when you run the Micropython firmware there, you're left with somehow like 25 kilobytes of RAM. So what I did at first, I just copied the library onto the board and tried to import it. And who would expect that? Well, it occurred that there is no memory left. So fact number 1, byte compilation, it's RAM. So ideally, I could pre-compile it on PC, as I had some embedded development background. The cross-compilation was just the first thought. And it's, so the cross-compilation is actually compiling the code on the architecture that it's not going to be run. But we usually use PC to compile the code for the microcontrollers, just to have it quicker, and sometimes just to make it even possible, because PCs have more memory. And it occurs that the cross-compiler actually comes with the Micropython itself. So it's called MPOI cross. And well, the plan was simple. Get the Micropython sources, compile the cross-compiler, compile the Micropython code with the compiler I just compiled. And it occurred pretty simple. It was compiling the cross-compiler itself was as easy as running the make command, and I ended up with the ready tool. I cross-compiled the module to the bytecode. I imported it, and it occurred that it works. It was just enough. The lack of RAM was not because of the size of the module, but rather because of the RAM needed for the cross-compilation, or for the byte compilation. So that was it. Let's print something. So to print something, we need to configure our serial connection and send the data. And fortunately, we have the machine module in Micropython that has the UART class, which is responsible for the serial communication. And the library already uses this UART class to communicate with the printer. And it gives us handy methods to just print things. It does it a bit like that. So we just need to instantiate the Adafruit thermal object, pass the serial parameters, and then you should end up with running with the object that will allow you to print anything on the printer. And guess what? It didn't work. But the error message was kind of confusing. It's extra keyword arguments given, so it's not that obvious. So it works well on low-pi. It doesn't work on ESP. And yeah, it occurs that implementation of UART for ESP doesn't support pins parameter. Well, if I had read the documentation first, I probably knew that. But, but yeah, it made me think that, yeah, hardware-related functions may have different APIs, even if they're named the same, and even if they are part of the standard library. So you need to be aware of that. And it came to the conclusion that, well, I should probably never assume that the code that ran on one hardware is actually going to run the same on the other hardware, even if they both claim to run MicroPython and they are not using anything apart from the standard library. So it made me think that I should test it on more hardware, but I ended up with a solution. So I tried to move the platform-dependent code to a separate module and make it as invisible as possible. So I ended up with creating some kind of a class that's actually constructing the UART object and putting it to a attribute of the class. It uses the sys platform. Sys platform is a string that's identifying the platform you're running. So for microbit, it is microbit. For lowpi, it's lowpi, Pascal case. For ESP, it's ESP, etc. So maybe it's not beautiful, but I had it in the separate module and ended up with something like that. So I just constructed, get the UART port, and, well, it worked. Sort of. And it worked. And I just spotted that, well, I'm actually having a problem. It was by no means the speed that I've seen on Raspberry Pi, and by no means it was the speed that I've seen on LowPi, which was kind of confusing. So after looking to the code, I spotted the suspect. So yes, there is a very simple way to work with the buffer underrun, buffer overrun, actually, which is based on time. And it used the microtime function. It adds some interval, which is calculated with the length of the string, and then it waits for some time to make sure that the buffer is empty. So this is the method writeBytes, which is actually using it. So it calculates, well, before running this method, it calculates the 1 byte time, which is a fraction of a second. So yeah, it occurs that the time function on ESP returns seconds as an integer. So the resolution that I had was actually in terms of seconds, not the fractions of seconds. So it occurred that I was waiting at least 1 second between loading data to the buffer, which was kind of confusing, because when I tried the very same method on the Unix part of the MicroPython, it was returning floats. So yeah. However, I must admit that, again, I should have read the documentation. It says that you shouldn't expect anything more than a second resolution, and you should use the appropriate precision for your program, and you should use ticks milliseconds or ticks microsecond function that will give you just the appropriate amounts with the appropriate granularity. So another lesson learned was that, well, functions that look familiar in CPython doesn't actually behave the same. And I learned somehow not to fully trust the Unix MicroPython port. So reading the manual, yeah, definitely I should do that, at least more than I've done. And I should use the appropriate APIs. So I should use the ticks millisecond to measure the time and use the appropriate methods for adding and getting the difference between the time periods. So the documentation states that I shouldn't use the normal operators like plus, minus, and all the others. So I ended up with something like that. So I used this add to get the time calculated. I used the tick diff to calculate the difference. I ran it, well, and it worked a lot quicker. However, there was still a slight speed difference between the LowPy and the ESP8266. The problem wasn't as big as it used to be, and it also left me with the thought that I had before. Why, before, the LowPy was actually running normally when I was having the 1 second resolution? So I again started looking into the code. And I found the suspicious code, the same actually again. And while I was thinking about it, I just thought that the tick diff looks a bit fishy. And so I made a little experiment. So I put 2 timestamps and tried to find the difference between them. And this is how it works on LowPy. This is how it works on the ESP. So it occurs that the Micropython implementation on LowPy takes the arguments in a different order than the official ESP8266 port. Well, again, documentation states that, but I wasn't expecting that at all. So even if the API is the same, functions may behave differently. So I came up with an idea to write a wrapper that would detect the actual behavior and swap the parameters if needed. And again, I was left with the thought that I should test it on as many boards as possible. So I ended up with something like that. So at first, I just tried to see if the difference of some well-known values is negative or positive. And based on that, I'm actually using the appropriate arguments order. And I ended up with something like that. So I just added a property or the actual. I added the property that's a function that's going to be used for calculating the difference, and it uses the appropriate implementation. And then it actually appeared to work. So summing up my findings. Well, the Micropython is not actually the Python you're accustomed to. It has its different behaviors. It was kind of clear from the very beginning, but not in the very detail. Micropython implementation for different hardware platforms may actually and do differ. I've just came through 2 of them, but there are even more differences between the other platforms. Yeah, embedded devices resources are rather constrained. This is a cliche, but yeah, you should actually use the cross-compilation and module freezing whenever it's needed. And you should never trust your gut feeling, even if the API looks somehow familiar or you're pretty much sure how it should be used. you should read the docs and probably read the code, or maybe both. And I still have the impression that creating the code that is possible to run on different hardware devices is kind of a challenge in Micropython. So you should probably test it on as many devices as possible. It's highly likely that you do not own all the devices, so maybe it's a good idea to share your code with the others and let the others also do some testing. Before I say thanks, I would give you a small idea of the next part. So the question that rises, there was a microbit when I was talking about the UART. And I don't have it fully running yet, so I wasn't showing the code, but still, I got the UART working. So this is how you instantiate UART on ESP. This is how you instantiate your LowPy. This is how you instantiate UART on microbit. So it occurs that microbit actually doesn't use the machine module to control the UART. And UART is not actually a class, but a module on microbit. So it's a slightly different approach. And all of that boils down to a conclusion is if the Micropython actually, the Micropython name should be used on so wide variety of devices. I do not have an answer for that question yet. So, yeah, this is the end of my talk. This is the end of the problems that I stumbled upon during my playful hacking with the different Micropython boards. So thank you for the attention, and it is time for questions now.
Any questions?
With the different implementations, particularly the microbit implementation at the end, can you talk about performance differences?
Well, actually, the thing I was using was the UART, so there's no significant performance difference between the boards because I wasn't actually using the CPU power on that. Well, if I was, well, the obvious thing is that the processor on the 8066 is well, the lower grade than on the others, so it would probably affect it. But as far as the serial communication is concerned, it's not actually using the CPU power.
Any questions? Okay.
Is there a particular board that you would recommend?
Well, I think that when it comes to developing a project, I would stick to the ones that have the official Micropython ports. As although the different vendors seem to have the language that's still called Micropython, they tend to differ. So the ones that are on the micropython.org website, like the ESP8266, ESP32, STM32, I think that I would stick with these ones.
Any more?
Kind of almost a statement, but one of the things we're looking at for the roadmap to 2.0 for Micropython is to consolidate the APIs to try to make them all similar across the ports. Now, I think you ran into a few problems with LowPy because, yeah, it's not supported, and they've gone and done their own things for a lot of things. So UART in particular, for, as you mentioned, the supported boards is in pretty good shape in MicroPython. But yeah, you're right. I don't know how to deal with the MicroPython label being applied to things that are not coming out of mainline. It's a tricky thing. So, but yeah, it's good that you've mentioned all this, because it lets weight to us pursuing the API consolidation across boards. So.
Yeah, actually, I was thinking that maybe specifying the API and maybe doing something similar as Google does. Like you cannot call it Android till the moment it suffices some at least some conditions.
Yeah, no, something like that would be great. Yeah.
Thanks for the talk. It was really good. Do you find, because I haven't played with the cross-compiling at all, does that make any huge impact into your debugging process when you're finding stuff like this?
Not really. Well, I wasn't actually using debugger there, but it's still bytecode, not the machine code. So when you're getting an error, it tells specifically in which line the error was. So it's not really affecting that.
Anyone last? No? Okay. Thank you, Michał.
Thank you.
This is